Alright then, so now that we've gone over right triangle trigonometry, we want, or at least the basics of right triangle trigonometry, we want to introduce something called unit circle trigonometry. And so, as I discussed before, 1 second. So as I've mentioned before, this is a unit circle, or it's called a unit circle, because in essence, this is just a circle centered at origin in like a really nice place that has a radius of 1. So circle because it's a perfect circle, unit because it's centered at this point, 0, 0, really easy to work with, and has a radius of 1. Now, before we learned sine, cosine, and tangent in terms of the ratios of sides of right triangles. But there's one other very common in terms of the ratios of sides of right triangles to their angles. So if you had, say, a right triangle like this, you had an angle, theta, here, then the ratio of, let's say, the opposite to the hypotenuse would be sine of theta. Now, there is one other very common, and in fact, maybe even more common way to define trig functions, or trigonometric, what we call trig functions or trigonometric identities, that has to do with this unit circle. And so, I'm just going to show a point on the circle. And one thing to note is that this point right here is called, has the coordinates of cos x and sine of x, where x is just this angle right here. And so this is our other definition of cosine and sine. So the cosine equals x coordinate, and the sine equals the y coordinate. And so this is a very useful definition because one, we're still thinking about angles, right? So the angle is always measured from this horizontal line, the x-axis, all the way to this line right here, from this origin point to the actual point we're looking at. And now, one thing to note is that this is on a circle, right? And so, how do we show that this sign is related to this sign? Well, what we can do is we can draw the leg of a triangle from that point to the bottom. And because we're dropping just the leg up to here, it's going to be a right angle, right? Now, because this is a unit circle, this, the length of this leg right here is going to be 1, so the hypotenuse is going to be length 1. And now here's where it gets a little bit interesting. So remember that the cosine of x is equal to, in this case, the adjacent over the hypotenuse, right? So that would be this side over this side in this diagram. In this diagram, the angle is here, the right angle is here, and so the adjacent would be this side. And so the adjacent over the hypotenuse would be the length of this side over 1, right? But that would just be the length of this side, because anything divided by 1 is itself. And so the length of, say, this side is equal to cosine of the angle x. And by the same logic, sine of theta, or in this case sine of x, is equal to the ratio of the opposite to the hypotenuse, but since the hypotenuse is 1, in this case, sine of x would be equal to the ratio of this side to 1, which is just this side. So the length of this side is sine of x. And this is why it's very useful to also be able to represent the length of the side as the hypotenuse times length of sine or cosine. So this is how we define cosine x and sine of x for using a unit circle. And part of the reason why this is useful is because you can actually define sine and cosine of angles greater than 90 degrees. If you imagine a right triangle with a different right angle, well, how would that work? You would just end up with a shape like this, and there's no way you can actually connect these two sides without making a fourth side. And so when you're just thinking about angles in a shape, you actually can't do sine or cosine of angles greater than or equal to 90 degrees. But if you're not thinking about angles, but instead how far you're rotating around a circle, then it's very useful to, and very possible to, think of sine and cosine for angles greater than 90 degrees, because we can just go a little bit further and take, let's say, go to a point here, right? And so we can take, you don't need to do a different color for this. So we can take that and then measure the angle from here to here, which would be over 90 degrees. Or, because we're talking about rotations, over pi over 2 radians. So this is how we define cosine and sine in the context of the unit circle. So if you imagine a point on the unit circle, so this point, 0.415 and 0.9098, then if you imagine drawing a line from the, whoopsie daisy. If you imagine drawing a line from this origin to whatever point here, then the angle made between the x-axis and that line has the cosine of the x value. In this case, it would be the cosine of whatever, the cosine would be equal to 0.19, and the sine would be equal to the y value, which in this case is 0.98, not 18. So as we look at, so if we were to look at the sine of, what would this angle be? Well, it's a 90-degree angle, right? And so the sine of 9 degrees, or pi over 2 radians, is equal to, what is the y-coordinate? It's 1. Now, what is the cosine of pi over 2, or 90 degrees? Well, if you look at the x-coordinate, it's 0. And therefore, we can say that cosine of pi over 2 is equal to 0, and sine of pi over 2 is equal to 1. And note that we can actually extend this even further when thinking about the cosine and sine of, let's say, this point. For this point right here, the cosine would be 0, but the sine would be -1. And what angle is this? Well, going around one quarter circle, it's pi over 2. Going around another, that's pi. Pi over 2 plus pi over 2 is equal to pi. Going around another, this would be also 2 pi over 2. Going around another pi over 2, or another quarter circle, we would go to 3 pi over 2. Therefore, the cosine of 3 pi over 2 is equal to 0, but the sine of 3 pi over 2 is equal to -1. And so that's a very useful way of thinking about sine and cosine. And so just remember that if you're having trouble thinking about how exactly the sine and cosine of a unit circle relate to the right triangle sine and cosine, then drop a leg from the point you're looking at to the bottom, and then think about the triangle and the angle right here. So remember that adjacent over hypotenuse, when the hypotenuse is 1, that's just this, and that's going to be cos. And opposite over hypotenuse, and this one, hypotenuse is 1, is just going to be sine And so this is so the height of this triangle is going to be the y coordinate, which is sine of x, and the length of this triangle is going to be the x coordinate, which is cosine of x. Now let's go ahead and take a look at, I'm just going to clear everything on screen. Let's go ahead and take a look at what happens if we maybe move around the point a little bit. And so if we move it to the other side, let's go ahead and say we want to consider second. Don't think too much about all these numbers and equations on the left side. They're just there for the sake of visualization. So let's go ahead and say we look at this point right here. So if we try and use the method that we just did, we can drop a leg here. And one thing to note, so the angle we would actually think of when we're doing right triangle trig here is this, but the angle that we think of when we're talking about actual unit circle trig would be this. So this would be the angle x that we would think of, and this would be the angle theta that we think of for when we're talking about right triangles or angles. And so in this case, the angle theta is 45 degrees. Or what is 45 degrees? Well, 45 degrees is 1/2 of 90 degrees, and 9 degrees is equal to pi over 2 radians, or 1/4 circle, and therefore 45 degrees would be half of that, and half of a quarter circle would be 1/8 of the circle. And so this would be pi over 4 radians. This angle right here would be pi over 4 radians. And this angle right here would be, well, you go pi over 2 plus, because this thing is 1/8 circle, this must also be 1/8 circle. So what is pi over 2 plus pi over 4? That becomes 2 pi over 4 plus pi over 4. And so this whole angle, x, is equal to 3 pi over 4. And so now one thing to remember is that we're looking at points in different, we would say, quadrants. And so in this quadrant, the x value is going to be positive, it increases to the right, and the y value is going to be positive, it increases upwards. So this quadrant is positive x, positive y. This quadrant, the x value is actually negative, but the y value is still positive. In this quadrant, the x value is positive, but the y value is negative, right? So you're going downwards, but to the right. And in this quadrant, the x value is negative and the y value is negative. So they're both decreasing. Now, if we were to just think of cosine of 3 pi over 4, what we could do is we could first think of, well, what would say the length of this side be in a right triangle where the angle is pi over 4. So these two angles are what we call supplementary, and because of that, they have a very important relation, because they add up to this pi angle, or 180 degrees. If we were to just calculate out the things for this triangle, well, remember that the hypotenuse is 1, and one thing to note is that this is still 9 degrees. So this is 9 degrees, this is 45 degrees, and so what must this angle be? Well, the sum of this angle and this angle must be equal to 180 minus 9 degrees, and so it's 45 degrees plus this angle must be equal to 9 degrees. Therefore, this angle is equal to 45 degrees as well, and so the two angles are equal. So these two angles are the same. And what that means is that this triangle is what we call an isosceles right triangle, which is to say that the length of this side and this side are the same. or sine x, or sine theta rather, is equal to cosine theta. And so how does this help? Well, remember again that the hypotenuse is equal to 1. And therefore, we're looking for a number such that, let's go ahead and say this side is equal to a, and this side is also equal to a. We're looking for a number such that a squared, a times a, plus a squared, a times a, the square root of that is equal to 1. And so, if we go ahead and try and get rid of the square root by, you would say, squaring both sides, you get is a squared plus a squared is equal to 1. So 2a squared is equal to 1. And then you would divide both sides by 2 to get a squared is equal to 1/2. And then we would take the square root of both sides. And so offhand, it looks like our answer is a equals 1, a is equal to the square root of 1 over 2. This is the same thing as saying the square root of 1 over the square root of 2. And since the square root of 1 is 1, this becomes just a is equal to 1 over square root of 2. Should we write that? So we get that both these sides are equal in length to 1 over square root of 2. Now, remember that when we're dealing with fractions that have these ugly square roots in their denominator, oftentimes teachers will get on you if you do not rationalize them, especially if they're teachers that grew up with older textbooks and whatnot. And so, to rationalize denominator, you want to multiply by something that and both the numerator and denominator that will cancel out the square root. So in this case, you have a square root, and so you can multiply by that square root, because a square root, by definition, multiplied by itself, is equal to the number inside the square root. The square root of 2 is defined as the number that multiplies by itself to equal 2. So if we multiply by root 2 over 2, root 2 over root 2, what we get is, well, this denominator just becomes 2, and so we get root 2 over 2. And so, as far as the teacher would be concerned, the cosine of 3 pi over 4, the cosine of pi over 4 is equal to root 2 over 2. And because this is the thing where we set sine of theta equal to cosine theta, this is also equal to the sine of pi over 4. Now, you might be noticing that in this case, I computed the cosine and sine of theta, but not of x. And part of the reason I did that was because when you have a triangle, of course, you can't have a triangle where one of the legs has a negative length. That just doesn't really make sense. But if you're just thinking about a point on the unit circle, of course it can have a negative coordinate. Why not? And so what we have to consider here is that although cosine of pi over 4 is equal to root 2 over 2, if we were to look at the actual x value, or the actual x here, cosine of x, cosine of 3 pi over 4, is actually equal to, well, look at this here. Here, the x value is negative, but we just showed that the length of this side has to still be root 2 over 2. The length of this triangle leg has to be root 2 over 2, but the actual x value has to be negative. Therefore, cosine of 3 pi over 4 is equal to negative root 2 over 2. But what is the value of sine of 3 pi over 4? Well, it also has, now, the absolute value also has to be root 2 over 2, because we said that the length of this leg has to be root 2 over 2. But because in this quadrant, the y value is positive, it would actually be positive root 2 over 2. And so, in short, we can have the cosine be negative or the sine be negative if the sine is in, say, this quadrant or this quadrant, or we can have them both be positive. But if we're just looking at the right triangle, then we're only going to be considering angles from 0 to pi over 2. And therefore, if we're doing right triangle trigonometry, we're always going to get positive and positive sine and cosine. One other way to think about this is, do you remember, is look back at when we said a squared is equal to 1/2. Now, one of the solutions to a squared is equal to 1/2, a squared is equal to 1/2, is a is equal to square root of 1 over 2. But the other solution is that a is equal to negative square root of 1 over 2. And why is this? Well, let's go ahead and see what happens if you multiply this by itself. Negative root 1 over 2 times negative root 1 over 2. What do you get? Well, this becomes root 1 over 2 times root 1 over 2. And by definition, this is equal to 1/2, right? But think about what happens to these negative signs. Negative 1/2, negative something is equal to negative 1 times that something. And so this is equal to negative 1 times root 1 over 2 times negative 1 times root 1 over 2. So this becomes negative 1 times negative 1 times that. And this whole thing just cancels out. And so, because when we multiply a negative number by itself, it becomes a positive number, that means that when we're taking the square root of, when we're saying that something squared is equal to another thing, we can sometimes consider the positive and negative square roots. So, depending on where you are in the unit circle, you can have a positive or negative cosine and sine. Now, thus far, we've been talking about cosine and sine, but we haven't really talked about that last other trig function, which is tangent. And the reason we haven't talked about it is because first we needed to establish sine and cosine. And so let's just go ahead and go back to a nice, let's do something like on this side. So let's go to something on this side. And so let's go ahead and draw that triangle down. So you have this angle, x, which would be equal to theta in this case, because it's and we have this is equal to cosine x, and this is equal to sine x. And the hypotenuse is equal to 1. Now, remember that tangent is equal to the opposite over the adjacent, right? Because so ka toa. But as we just saw, when we have the hypotenuse is equal to 1, we get that the adjacent is equal to cosine x, and the opposite is equal to sine of x. Therefore, tan of x, or tangent of x, or just tan of x, sorry. Tan of x is equal to sine x over cosine x. And this is actually a very, very important identity. It comes up quite a lot. One other way to sort of think about this is you see how we have a sort of line from this origin to this, sorry, 1 second. How we have a line from the origin to this point on the unit circle right here, right? So if you think of the sine of x as being the y coordinate, and the cosine of x as being the x coordinate, then you can say, well, remember how we compute the slope of the line between 2 points. So if we have sine of x and cosine of x, then we would do the y-coordinate of this point minus the y-coordinate of this point, divided by the x-coordinate of this point minus the x-coordinate of this point. So that would be equal to, the slope of the line is equal to sine x minus 0 over cosine x minus 0, which is equal to just sine x over cosine x, which, as we just saw, is equal to tangent of x. And so a very, very nice way of thinking about tan of x is that it is the slope of a point on the unit circle. It is the slope that you need to actually get to that point. And so that is one of the more elegant ways of thinking about tan of x. So let's just summarize. When we have a right triangle, you can think of cosine and sine for an angle between 0 and 90 degrees as being opposite over sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and tangent as being opposite over adjacent. When we try and define cosine x and sine of x with a unit circle, we can think of a triangle that uses these definitions very similarly, and we get that the cosine of x is equal to the x-coordinate of the point, so then the x-coordinate of this point right here. Sine of x is equal to the y-coordinate of this point, the height of the triangle, and tangent of x, or the opposite over the adjacent, is equal to the slope of the line to the point on the unit circle. And when we use the unit circle, we can think more easily about rotations, so we can go around the circle more easily, and we can think of cosine and sine of angles greater than pi over 2. And so that's kind of the crux of most unit circle trigonometry. And before we end off, there is one last thing I'd like to mention, and that is, remember the distance formula between 2 points. So the distance formula between 2 points is going to be equal to the difference between the x-coordinate squared, the difference between the x-coordinate squared. So let's go ahead and call that the difference in x squared, plus the difference in the y-coordinate squared, and the square root of that. So if we have, what is the difference between, let's say, the x-coordinate here and the x-coordinate here? Well, that's going to be cosine of x minus 0 squared. What's the difference between the y-coordinate here and the y-coordinate here? That's going to be sine of x minus 0. And if we just kind of square both of those, then we get that cosine squared x. Okay, so one slight bit of notation. So when we say cosine of x squared, this is the same as saying cosine squared of x. And so this is just because sometimes it's a little bit more convenient to write the squared on the inside. So just don't get confused when I write something. So that means that cosine squared x plus sine squared x, the square root of that would be the distance from this point to this point in the unit circle. But what is that actual distance? Well, because it's a unit circle, and this is the radius, it's going to be 1. That means that the square root of cosine squared x plus sine squared x, the distance between those points has to be equal to 1. And if we multiply both sides by themselves, if we square both sides, to get rid of this square root, you just get 1 times 1 on the right side, and you get rid of the square root on the left side, then what do you get? You get cosine squared x plus sine squared x is equal to 1. And this is a very useful identity. It can come up a fair amount. So that concludes the section on introducing unit circle trick.